Hi, Calc 1 students. Welcome to your first flipped class video for the semester. So as you are watching this video, you should be taking notes. You can either print the video notes from Canvas or you can just take notes on a lined sheet of paper. It's okay if you don't have a printed copy. Take notes for yourself. And then after you watch these videos, you're going to upload those video notes to Canvas. So that's how these videos are going to work. If you have any questions about the videos before class, feel free to send me emails, and I'll also answer any questions at the beginning of class. Remember that what we'll do in class is work more problems based on this information. So hopefully you understand it after you watch the video, but definitely understandable if you have questions as well. So what we're going to do for our first set of notes here is try and understand our big goal for the semester. Like that's what we're going to do the second class day is understand what we're doing for the whole semester, which is fun. And we're going to try and make this a little more algebraic than we had and graphical than we had in class last time. So we're going to still have that same question. We still have Bob driving his stunt car. But now instead of having a video of his position, we have a function. Not something that happens in real life usually, but in math, we like to simplify things a little bit. So we've got this function here that I've given. F of t is -1/2 t squared plus 4t. This telling us how far Bob is from his starting point at any time. So if I plug in 0 into that, I get 0 out. That tells us that at 0 seconds, he was at his starting point. If I plug the number 4 into that, I get 8 out. That tells us 4 seconds after he started moving, he was 8 units away, which I guess I measured it in meters, so 8 meters away from his starting point, okay? So I've got the graphic given below, and so we notice based on the upside down parabola shape that what's happening here is that he's moving away from his starting point, and then he actually comes back to his starting point. So at 8 seconds, he's back where he started because his position is 0. 0 was his starting point. So none of that's the calculus part, but it's useful to understand what this graph is telling us. So the question that we're actually asking here is what is the instantaneous speed of Bob's car at t equals 2? So if you looked at his speedometer at 2 seconds, what would it be reading? How quickly is he moving? We know that speed should be measured in meters per second. So we're looking for something that's in meters per second. And you might ask yourself, what is that on the graph? So this is what we were estimating in class last time by using smaller and smaller average speeds. And we're going to do a same idea, but we have to figure out what that looks like graphically. If we think about what we did in class, we were finding average speeds or over smaller time intervals. So we are looking for the instantaneous speed at t equals 2. And if you think about what that is, that's the slope of the line at this curve. So what we want is we want the slope of this line. Whoops. So this is the line that barely touches the curve at that function, or touches the curve at that point, and goes through the point that we care about. And so it should actually touch the curve. So probably looks a little more like this. Okay, so we want the slope of that line. Ask yourself, why can't I just find the slope of that line? Why do I have to estimate this? Okay, ask yourself that question. The answer to that question is that we only have 1 point. To find slope of a line, I need 2 points. And maybe I could try and guess what another point is on that line, but I don't know it exactly, so it's still going to be an estimate. So I need 2 points in order to know the slope of a line. So let's pick another point, and let's pick a point on this curve. And this is what you were doing in class when you were doing those smaller and smaller time increments, okay? So let's pick another point on this curve, and I'm going to pick the point up here where t equals 4, just because that's an easy number to work with. This is farther away from 2 than we would normally use. And so what I'm going to do is I'm going to draw the line between these 2 points on the curve. I know exactly what those 2 points are because they come from that function I'm working with, so I actually know what they are. And so I can find the slope of that blue line. That blue line approximates the black line. It's not a great approximation, but it approximates it. Okay, so let's find the slope of that line, and I'm going to try and break this up. So I'm going to put a time interval here. So my time interval is from 2 to 4 seconds. Think of that as an interval notation. So I'm starting at 2 seconds, ending at 4 seconds. And I'm going to ask what's the average velocity or the slope of that line. And so to find the slope of the line, I need the y values. The y values are coming from my function here. So I can plug 4 in, and I can plug 2 into my function. So I'm plugging 4 into my function, that gives me f of 4. I plug 2 into my function, I get f of 2. And then to find the slope, so that's the change in y values. To find slope, I do change in y over change in x. So that's 4 minus 2. Okay, f of 4, when I plug 4 into this function, I get 8 out. When I plug 2 into that function, I get 6 out. You should double check and make sure my math is correct there. So I'm going to get 8 minus 6 over 4 minus 2 is 2. And that gives me 1 out. So 1 is the slope of that blue line. It is a bad estimate for the slope of the black line, but it is an estimate. Okay, let's make our estimate better. So let's pick a number that's closer to 2. And I'm going to pick like 2.1, which is really close, but let me draw like, so if I pick a point here, which is closer to 2, the x value is closer to 2, and I draw the line between my black point and my red point, that red line is much closer to the black line than the blue line was. So that's a better approximation for the slope of my black line. So that's why I'm going to pick a number other than 4 that's closer to 2. And let's pick something that's really close to 2, like 2.1. So let's find the slope of the line between 2 and 2.1. So the 2 and the 2.1 are my x values. To find my y values, both of these points lie on my function, so I have to plug them into the function. So to find the slope, I do change in y over change in x. So my y values are f of 2.1 minus f of 2 over 2.1 minus 2. I need to plug 2.1 and 2 into that function, use a calculator, and then divide by 2.1 minus 2, use a calculator there. I get 1.95 out, okay? And then go ahead and try these calculations on your own. So follow the same process and find the slope. Let's pick numbers that are even closer to 2 than 2.1. So how about 2.01 and then 2.001? So find the slope of the line between each of those points. These are going to be even better approximations of that black line. And go ahead and do that on your own and pause the video here. I'm getting 1.995 and 1.9995. Okay, so these are all approximations for the slope of that line that we care about. The slope of that line that we care about gives us the instantaneous speed. So we ask ourselves, as these points that we're picking get closer to the point that we care about, what are these slopes getting closer to? What are these values getting closer to? Well, they certainly look like they're getting closer to 2 to me. So our average velocities get closer to 2. So that means we're going to estimate his instantaneous speed to be 2 meters per second. Okay. This process is a little funky. If you're confused about it, ask me in class. Please come with all the questions you have. I would love to answer all of them. But before you do that, there's going to be one more video with another example and some terminology, okay? The idea to keep in the back of your mind with all of these problems is we're trying to estimate the slope of a line at a single point. We can't do that because we only have one point on the curve, not 2 points. So we pick another point on the curve that's close to the one we care about. We find the slope of that line. That line is an approximation. It's close, not perfect. So we pick a few points that get closer and closer to the point we care about. Those are all approximations, but we can use those approximations to guess what the actual value might be. And this is our long-term goal in calculus, is to not have to guess anymore, but to actually get a real answer.